name's Anna. I'm a developer at Carbon5. We build digital products for all kinds of companies, growth, enterprise, startups. We have offices all over the country. Like everybody else here, we're hiring, so if you're interested, talk to me later. Today I want to talk a little bit about crypto, a little bit about exchanges. So I'm not working at Carbon5. I'm trying to get better at climbing rocks without hurting myself. It's a lot of fun. Shameless plug. It's a podcast that I do with a couple of folks that are here, Amos King and Chris Keithley. It's called Elixir Outlaws. Feel free to check it out. Another shameless plug. A couple of years ago, I started a nonprofit called Elixir Bridge. We put on free workshops for underrepresented folks in tech to learn Elixir and Phoenix. We have a workshop happening tomorrow. If you're interested, there's still space. Come talk to me later. So what do I want to talk about today? Talk a little bit about Bitcoin and the blockchain, how it works, why we care. And then after that, I want to talk a little bit about what is an exchange, now that we know a little bit about how cryptocurrency works. And then why would you try and model that in Elixir? So what is Bitcoin? So if you were to Google on the internet, you'd probably find a definition that says something like this. Bitcoin uses the blockchain to implement a decentralized ledger for payments. If that doesn't make sense, don't worry. Hopefully by the end of the talk it will. Otherwise, I will not have done my job. Folks also refer to it as a secure and anonymous store of value. So I want to take a step back and talk a little bit about what is value, and talk about it in the context of something that is more familiar to us, which is money. If we look at the definition of money, it's something that we can exchange for goods and services. We can pay our taxes in it. We can pay down debts. But what really determines its value, right? If we look back in history, the first kind of dollars or banknotes came to being in the 17th century in Stockholm, and they were backed by gold and silver. And if we fast forward, post-World War II, the Allied countries got together. There was an agreement called Bretton Woods, and they decided we're all backing our currencies by gold. So why gold? Or why precious metals? Well, they're durable. They are arbitrarily divisible. There's a level of scarcity. And you can exchange them for goods and services. So back to Bitcoin. The big idea behind cryptocurrencies is that for the first time, we can do a completely digital transfer of value over the internet without anything backing. And how does it get its value? Well, the same rules apply, right? There's a level of scarcity. You can't really pay your taxes in it, but you can exchange it for goods and services. And this last point, and I didn't mention this when I was talking about the dollar, but people were betting on the dollar because they believed in the strength of the US economy. So they're betting on the future. And in this case, a similar thing is happening, right? Folks are betting on the future. So there's also this idea of anonymity and security tied to cryptocurrencies. I want to take a moment to talk about that. That plays a big role in how the cryptocurrency actually works. So if we talk about cryptography, and we look at the history of cryptography, especially in this country, it was really just an admission of the government or the military up until the 1970s. And really it was an admission of the military until about 1999. And early cryptographers wanted to use cryptography to help break the monopoly of the state. They really believed in an individual's ability, or an individual's right, essentially, to maintain privacy and anonymity. And with the advent of computers, they became more and more concerned about an individual citizen's ability to protect their own privacy. So I don't know if any of you are familiar with this photo, but this is a group called the Cypherpunks. It was started in the early 90s by Eric Hughes, Timothy May, and John Gilmore. And the premise of this group is they also strongly believed in individuals' right to privacy and anonymity. And just because somebody wanted to remain anonymous did not mean that they had something to hide. They started a mailing list, they had a huge number of followers, and in 1995, Eric Hughes released what's called the Cypherpunk Manifesto. And essentially it said privacy is absolutely necessary in the digital age. Governments and corporations are not going to do it for us, and that we have to do it. And not only do we have to talk about doing it, we have to write the code to actually do it. So a lot of the cypherpunks actually built tools to help people maintain privacy and anonymity. And many of them made early attempts at digital currencies that were not successful. One of the more famous attempts was called Hashcash. And while this attempt didn't succeed, the entity that released Bitcoin, Satoshi Nakamoto, was influenced by Hashcash, the concept of proof of work. And if you don't know what that is, don't worry, we'll get to it in a little bit. So we fast forward again, 2008, the economies all over the world crash, and this conversation that had been happening in the cypherpunk community gets revived. And this conversation is about having an alternative store of value outside of the government. And so while it had been percolating, in 2008 it really escalated, right, given what had happened. Coincidentally, Satoshi releases Bitcoin in 2009, right, an alternative store of value. And he defines it essentially as a cryptographic proof that allows folks to make transactions, secure and anonymous transactions, without the need of a middleman. Okay, so how does it work? Well, we talk about it being decentralized. All that means is that there are nodes all over the world communicating with each other. And they each have a full copy of the blockchain. And we can talk about the blockchain. In this case, we're talking about Bitcoin and Bitcoin's blockchain. They have a full copy. You can think about it as a ledger, right? It's essentially just a list of transactions, the way you would think about your bank ledger. And they communicate via something called the gossip protocol. And I really like this analogy of how gossip spreads information. It's, synonymous with, or analogous to how epidemics spread or how social networks disseminate information. Right? A node will communicate to its peers, that communicates to its peers, and eventually that information propagates across the network. And this is what it might look like. So before we talk about how we actually create transactions and send them to the blockchain and add them to a block, I want to take a moment and talk about asymmetric cryptography, right? Public and private key pairs, because that plays a big role in how we actually send money on the blockchain. So as an example, if I wanted to send Ben 10 Bitcoin, I have as my identity, right, on the Bitcoin network, I essentially have a public and private key, right? That's how people identify me. They'll identify me by my public key. And so what I'll do is if I create a transaction, I'm going to sign it with my private key and then send it along with my public key. And then when Ben gets it, he can use my public key to decrypt the message and know that it hasn't been tampered with. And there are no concepts of accounts on the blockchain, right? We're talking about Bitcoin. When you buy, like let's say you go on Coinbase, you buy 10 Bitcoin, there's going to be a transaction written somewhere on the blockchain saying I have bought 10 Bitcoin. Then, if I say, let's say I want to send 5 of those to Ben and send 5 back to me, I'm going to take that initial transaction and from that create a new transaction that says I have 5 and then Ben gets 5. And then that transaction gets written to the ledger. And this initial transaction, the first one, essentially is considered spent, can't be used anymore. But this new one is not considered spent yet. And these new transactions that we send onto the blockchain network are called unspent transaction outputs. The transactions get sent. They get put into what are called mining pools, like pools of transactions. And these nodes that are mining Bitcoin essentially choose which transactions they want to put in a block. A block can fit about 1 megabyte of transactions. And so how they actually add them is they take 1 megabyte of transactions and they hash them by 2s in what is called a Merkle tree until they get to a Merkle root. And what we know about hashing, right, is that the contents that go into a hash, if they change even slightly, then the output of the hash is drastically different. And so you can see that not only does it help prevent transactions from being tampered with as they're being hashed up to the root, but it helps nodes verify information. Because if one node has a different Merkle root than the other, they can go down the Merkle tree and easily see where something might have been tampered with. Okay, so we have transactions. We can add them to a block. And then how do we actually add blocks to the blockchain? So remember I referenced not too long ago this concept of proof of work, Adam Back's Hashcash. So the idea behind proof of work is that for miners to actually be able to add a block to the blockchain, they need to do a little bit of work. They solve an arbitrary puzzle. The network has something called a work factor, and that work factor varies so that there is a block mined on the Bitcoin network about every 10 minutes. And essentially that work factor is saying you have to solve a hash with X number of leading zeros. So if the work factor is 5, you have to solve a hash with 5 leading zeros. So what content are you using to hash? Well, we take the previous hash, like the root hash from the previous block, our hash, a timestamp and a nonce, right? And a nonce being an arbitrary value that increments, right? And so we increment all of these, we put these values together and then we increment our nonce and do this over and over and over again until we solve the puzzle. And if we're the first ones to mine the block, we send it out into the network. If it's the first block that's valid to propagate, it gets added to the blockchain, and then all of the miners start building off of blockchain length X plus the length of plus our block. And so what this does is it provides a way for nodes to agree on how the blockchain gets updated. And it essentially solves a problem of who gets to decide consensus, right? How we influence consensus. And the idea here, at least when Bitcoin was released, was that people were mining on their machines. They had the equivalent amount of hashing power. And so they had the equivalent probability of being able to mine a block. That's not really the case today, given that people have set up large mining rigs and your ability to mine is directly proportional to the amount of hashing power you have. But that was the intent. And this idea of consensus, right, this idea of mining off the longest block, so called Nakamoto consensus. Okay, so Bitcoin uses blockchain to implement a decentralized ledger for payments. So now that we know a little bit about what cryptocurrency is and how it works, let's talk about exchanges. So what is an exchange? Some of the bigger exchanges out there, right? Coinbase, Poloniex, Robinhood. Exchanges essentially allow two different parties to buy and sell, at least crypto exchanges, to buy and sell digital assets. There are two types of exchanges, centralized and decentralized. Decentralized exchanges don't actually ever hold on to crypto. They essentially allow for a transaction between two parties. They usually have something called a smart contract that executes, and that transaction gets written to the blockchain. Centralized exchanges, and I'm sorry this photo is so small, centralized exchanges actually control and hold crypto. And then when transactions happen, those transactions get resolved internally in their ledger. So let's say Alice had 1 Ether and Bob has 10, and Bob's going to send Alice 2. On a centralized exchange, what happens is that transaction would happen, and both of their accounts would reflect that that transaction happened. But the exchange would resolve that transaction internally with its ledger and not actually send a transaction to the blockchain. And a lot of these centralized exchanges actually hold a lot of crypto in cold storage, which essentially means they're putting it in a wallet that is not connected to the internet, essentially, right? Not connected to the network for safety reasons. The problem being is that if a centralized exchange gets hacked and the money gets stolen, there's no record on the blockchain of that transaction actually happening. So generally, you don't want to keep your money or your crypto, right? If you have it on a centralized exchange, you don't really want to keep it on the exchange for very long. You want to transfer it to a wallet that is not on the exchange so that that transaction does get written to the blockchain. So today, given that some of the exchanges that are out there, the larger exchanges, are centralized, we're going to talk about how you might model some of this behavior in a centralized exchange. And these are a couple of things we're going to build, right? We need some concept of accounts. We need a way to manage accounts. We need a way to place orders now that we have money or crypto in our accounts. And then once we have people who want to buy and have people who want to sell and those match, we need a way to settle those accounts and reflect those values accordingly. And those buying and selling, those pieces get listed on an order book, right? They're called asks and bids. So an ask is the amount I'm willing to sell for, and a bid is the amount I'm willing to buy for. And it looks kind of like this. Usually you have the top bid, the most I'm willing to buy for at the top of the bids list, and the lowest ask, the least I'm willing to sell for at the bottom of the ask list, and then the difference between the highest bid and the lowest ask is called the spread. Okay. So we're going to build an account, a way to manage them, we're going to place some orders, and we're going to settle our accounts. So before we get into that, I want to talk a little bit for those who are new to Elixir, right? All work that gets done in Elixir gets done in something called a process. Right? They're super lightweight, or all code that runs in Elixir essentially gets done inside of a process. They're super lightweight. You can run hundreds and thousands of them on your machine. They do not share memory, right? There's something called a scheduler on the Erlang VM that will optimize across your operating system processes. Processes I'm referring to in Elixir are different from your OS processes, and they communicate via message passing. Let's do a quick look at how message passing works in Elixir. Every process essentially has a process ID, a process identifier, and we can send messages to. And there are two functions, send and receive, that allow us to send messages and then process messages that we're receiving. Right? So in this case, we have a function, it's called greet. By name, we have this receive method, and it's going to match against the pattern match, right, against the arguments coming in, and if those arguments are right, we will get output. So in this example, we can start a process. We pass our module, the function name, and the arguments to a function called spawn. We get a process ID, and then we can send, there's a function send, to the process ID. And again, if those arguments match, we got receive method, right, then we will get output. So we're going to build our account. But for our account, we need a little bit more of a long-running process. For the purposes of this demo, we are going to store everything in memory. This is not something you would normally do, right? You would want to not just store it in memory, but store it to disk in some way. But in this case, we're going to store it in memory. So we need a long-running process where we can store state. For the purposes of the accounts, we're going to use what's called an agent, right? And agents are essentially abstractions around background processes that can store state. So if we look at our account, right, we're going to have a struct, it's going to have an ID, it's going to have a balance of money, it's going to have a balance of crypto. And to start it, we call agent.startLink. We pass it a function, and the output of that function becomes the state of the agent. And then we get a process ID that we can refer to later in return. And to retrieve the state of the agent, we call agent.get. To update it, right, we call agent.update and pass it again the process ID and the new function. And then the output of that new function will be the updated state. And in this case, we are just going to add crypto or subtract, depending on if we're buying or selling. So how are we going to manage these accounts, right? Now that we have all these accounts, we want to model them being able to place asks and bids, and we want those asks and bids to be sent to our order book, and then we want to find matches. So how are we going to manage all of this kind of client-server behavior? So this is where we're going to leverage a little bit of OTP, right? It stands for Open Telecom Platform, and it's essentially a set of modules and design standards that makes implementing this kind of more complex behavior much easier. And really the behavior that we're going to leverage, right, is called GenServer. It stands for Generic Server, and it allows us to implement this client-server relationship with a series of callbacks, and developers can choose which of the callbacks they want to implement. So we're going to have an account server. We're going to bring in this GenServer behavior. Use is a keyword that essentially is some metaprogramming, for those of you that in other languages are familiar with metaprogramming, to bring in that GenServer behavior. We're going to call GenServer.startLink, our module name, the initial arguments we're passing to it, and we're naming our GenServer so that it's easier for us to refer to it later. And then the callbacks that we're really using are handle info, handle cast, and handle call. And our initial state, right, when we call our GenServer, we're going to have some initial state. GenServers are long-running processes that will allow us to store state. So we're essentially just going to have a map with references to our accounts, to references to the actual process IDs of the accounts, so we know when an account dies and the number of accounts we want to create. And essentially we want to, when we start our GenServer for the accounts, we want to generate a bunch of accounts. So you want to have a function that says, hey, when you're starting, generate a bunch of accounts, which is what we're going to do. So we're going to send a request to ourselves, to our self process, right? With this argument, create accounts. And since we didn't specify the type of request, because it wasn't synchronous or asynchronous, the callback that is going to handle all the other requests is called handle info. So handle info is going to match against that argument. We're going to generate a bunch of accounts, and then we're going to update our state. And we're going to call the generate accounts function for the number of accounts we need to create. Our accounts are essentially just going to have an ID, a balance of crypto. Then we're going to find the account that we had generated, right? And we're going to monitor it. We're going to start it with, or we're going to create the account with an ID, some balance of crypto, and some balance of dollars. And then we're going to monitor it so that we can know when it dies or not. And then we'll update our state, so we'll have that information in our state. I'll go back for a second. So if you notice the last argument, right, we're updating our state. I actually didn't put this in this create accounts function. But all of our callbacks will always return state as the last argument that they're returning in their functions. So we're going to send a similar request once we've created our accounts, right? We want to be able to place asks and bids. And so we're going to do similar requests. So every 10 seconds or every 15 seconds, we're going to simulate somebody placing an ask or a bid. So we're sending a request to ourselves. We're going to have this handle info callback. It's going to match against the request that we're sending. So in this case, we're creating an ask. And notice here, this no reply in state. The state is the last argument that gets returned from our callback. We're going to create an ask. Essentially, we're going to find a random account, check the balance, and then we're going to send, to make sure that we have money that we can use for this, we're going to send that to our ask server. And notice here we're saying genserver.call. So call implies that we're making a synchronous request, and we're sending it, the module name is our ask server, and then the arguments that we're sending, which is essentially this argument to match against send ask and our account information. And then our ask server, right, we talked about callbacks being implemented. Since we're doing a synchronous request, the callback for handle call, for genserver.call is handle call. So we're going to match against those arguments, right? We have the arguments that are coming in, where the request is coming from, and our current state of our ask server. And our ask server is really just starting with a list of asks and the latest ask ID. So we're going to generate an ask. And assuming we have enough money to do so, because it's a synchronous request, we're going to send that reply back to our account server. And we'll update our own state with this new list of asks. Our ask is just a struct. It's going to have an ID, an account ID, some price info, the size, the fact that it's an ask, and the type of currency, in this case, Bitcoin. So once we get that ask back, assuming we actually get it successfully, then we're going to send it to our order book so we can place it onto our order book. And bids work in the exact same way. I'm just modeling the ask code just to show you an example. So our order book server, we're also using a gen server, again, leveraging this easy client-server relationship. Our order book server is also just going to have a struct for its initial state, a list of asks, a list of bids, and then a list of matches, where asks and bids match. So it's going to receive that ask, and it's just essentially going to update its state, right? Handle cast. So we said genserver.cast to our order book, which was a asynchronous request. So you can imagine the callback for that is going to be handle cast. We're going to match against the arguments that we have, and we're going to update our state. So now that we have these lists of asks and bids, we actually need to find where they match, right? So that we can actually have those transactions be fulfilled. So essentially every so many seconds, right, every couple seconds, we're going to have a process, again, we're going to call ourselves, it's going to check against matches. And again, there are matching algorithms vary greatly in complexity. This is a simple example for this demo, but an idea of how you might want to start thinking about this. And our request, right, that we're scheduling every so many seconds is going to essentially be a call, an asynchronous call to our gen server that we're already in, our order book server, to check for matches. And really, we're essentially looking for when an ask and a bid match. And what do we mean by that? Well, if I have, let's say, one person is selling Bitcoin for $8,000, one person is selling Bitcoin for $8,010, and I'm willing to buy Bitcoin for $8,015, right? One person is selling one, the other person is selling two, and I want to buy three. And my bid should match both of those asks. And again, matching algorithms vary very much in complexity. This one is really simple, but this is what we're doing. And then once we have our matches, we're going to send it back to our account server. It's going to enumerate through those matches and then update each of those accounts accordingly. So if we had sold crypto, right, we're going to get some money but have less crypto. If we bought crypto, we're going to have less money but have more crypto. So we have these long-running processes, and especially since we're running and they have state, and that state is being held in memory, we want to know when they die. And if they die, we want a way to be able to restart them, right? And in this case, this is where we leverage this concept of supervision, right? And we talk about supervision a lot in Elixir, and that it allows us to introduce this concept of fault tolerance to our applications. So when I talk about supervision, I mean using supervisors. So in Elixir, generally working with two types of processes, supervisors and workers. And supervisors are really just specialized processes that are solely used to monitor other processes. So in this case, none of our processes have interdependencies, right? We're not in a situation where one process needs another process to start up before it can start. So there are many different supervision strategies. But in our current state, all of the processes, long-running processes that we're using can work independent of one another. So in this case, we're going to have a supervisor watching them, and the strategy that we're using to restart them is one-for-one, meaning if one dies, please restart it, right? There are other strategies, but they're not necessary for our current use case. All right, so I have a quick demo. I put together an example of what might happen if we start our server with like 100 accounts. So as you can see, and the text might be a little small, but you can see there's asks and bids being placed, right? Checking if there's enough money to place the asks and bids. And the UI, again, this is just output to the console, but you get an idea of how you might simulate some of this. So hopefully, again, this was a little bit high level. Exchanges are very complex. We didn't really cover some of the settling transactions on the blockchain. There's a level of complexity there, maybe in a future talk. We just didn't have the time for this one. But hopefully you got a little bit of an understanding of how crypto works, right? What it actually means, why it has value. And then from the Elixir side, what are some of the benefits? When we talk about Elixir, especially for folks that are new to Elixir, what are some of the benefits? And how do we leverage some of these really powerful behaviors to build complexity, to handle some of the complexity that we have in our applications? And that's all I got.